Welcome to C&EN Uncovered. I'm Craig Bettenhausen. C&EN Uncovered is a podcast series from Stereochemistry. In each episode, we'll take another look at a recent cover story in chemical and engineering news and hear from C&EN reporters about striking moments from their reporting, their biggest takeaways, and what got left on the cutting room floor. In this episode, we're looking at a recent cover story about a CO2 abatement method called ocean alkalinity enhancement. That aims to use the world's oceans to remove more carbon from the atmosphere. Are Earth's vast oceans our biggest allies in the fight against greenhouse gases? Can we augment the power of nature to keep our planet alive longer? We'll put a link to the story in today's show notes. I'm here with C&EN Assistant Editor Fionna Samuels, who wrote the article. Hi, Fionna.
Hi, Craig. It's so nice to be here.
Yeah, good to have you. So for anyone that hasn't had a chance to read the story yet, can you give a brief recap of what's in the article?
Yeah, so basically I reported on a few different experiments, field trials specifically, that are happening around the world to look at how we can add alkaline substances to ocean water in order to help it draw down more carbon dioxide from the atmosphere. And all of this is in an effort to sort of stymie the worst effects of climate change.
And how did you get interested in this topic?
It actually started out looking at solar radiation modification or solar geoengineering, which is putting stuff into the atmosphere to reflect sunlight back into space. But it turns out that there are almost no field trials happening in that space right now because it's so controversial and the method is very questionable. But there is quite a few different things happening in the marine carbon dioxide removal space. So instead of reflecting sunlight to cool the planet, removing carbon dioxide to help cool the planet.
Interesting. So one of the things I noticed in your story is this experiment called Loch Ness. Tell me about Loch Ness. The experiment, not the Celtic sea monster, or both. I'm flexible.
So unlike the monster, I guess this experiment is real and it's officially happening. They just got the permit finally approved with the EPA. It's being led by a researcher at Woods Hole Oceanographic Institute. His name is Dr. Adam Sebhas. And what they're doing is they are releasing a solution of sodium hydroxide into the water and looking at where that alkaline water goes and measuring a whole bunch of different things to try to see if they can quantify how much carbon dioxide is absorbed by the water because of that increased alkalinity.
Seems too simple to be intuitive. Can you explain how would dumping a bunch of lye into the water do anything about carbon dioxide in the atmosphere?
Well, so carbon dioxide dissolves in water naturally. This is an ongoing geochemical process. And when the gas dissolves into the water, it quickly reacts to form carbonic acid, which then dissolves into different carbonate ions. And because it's an acid, protons. So that's why we get ocean acidification. And it was really interesting because many of the researchers that I spoke to for this story started off as researchers of ocean acidification. So the pH plays a big role in how much carbon dioxide can be absorbed and then sequestered in ocean water. And by raising the pH or making it more alkaline, not only are you sort of combating that acidification that happens with carbon dioxide dissolution, but you're also making it so more carbon dioxide can be absorbed and then sequestered as carbonate ions and bicarbonate ions. It's a little bit like magic, to be honest.
And what kind of scales would this need to operate on to make an impact?
Well, that's a great question. So right now, humanity is releasing carbon dioxide on gigaton orders of magnitude. So that's 1 billion metric tons. And our annual emissions are close to 40 billion metric tons. Obviously, we need to reduce emissions. That's number one. But there are certain sectors that can't be easily decarbonized. So aviation, agriculture, those cows are going to keep farting. So we need to do more than just radically decrease emissions. Scientists think we need to also start removing carbon dioxide from the atmosphere. But if we're thinking on gigaton scale of emissions, we want to probably remove gigatons of carbon dioxide. That would be great. We can't do that right now. We're not even to millions of metric tons. So one of the researchers, David Ho, had a really good analogy. He thinks of carbon removal like a time machine. So if you're thinking we're emitting 40 billion metric tons of carbon dioxide annually around the globe, and if we could remove 1 million metric tons with these carbon dioxide removal techniques, you would have had gone back 13 minutes in time. That's equivalent to 13 minutes of carbon emissions. So the scale is huge. And it's impossible to do it with carbon dioxide removal techniques alone. Emission reduction is absolutely vital.
So I can imagine getting sodium hydroxide on a laboratory scale. You can get it at the hardware store. But on that kind of scale, we're not just talking about that kind of material. Where are we going to get that much base equivalence, that much alkalinity?
Yeah, so now you're talking about sort of the life cycle of these sort of techniques. And there's actually a few different techniques. It's not just putting sodium hydroxide in the water. So with sodium hydroxide, the Loch Ness team is truly only interested in figuring out if ocean alkalinity enhancement is a viable solution. And so they're basically using the cleanest form of alkalinity in the sense that sodium hydroxide, they can be incredibly confident of what they're putting in the water. They can be very confident about the kinds of reactions that are happening. Sodium ions already exist in seawater. Hydroxide ions also exist in seawater, but obviously at a far lower abundance. And the pH, they very well constrained how the pH will fluctuate after their release and at different timescales after the release. That's why they're using sodium hydroxide. In the real world, you're right, sodium hydroxide is not necessarily a viable way to increase the alkalinity of these bodies of water because you would need vast amounts of it. And right now, a lot of sodium hydroxide is actually produced in chlorine chemical reactions when we produce chlorine for other chemistries happening. Anyway, other researchers are looking at alkaline minerals. So like olivine is a big one, and that would come from mining minerals around the world. We, humanity, different people are already sort of spreading these mined minerals on agricultural fields and elsewhere. So those sources of mineral alkalinity exist already, which is why these folks who are using minerals argue that that might be a better option. A third technique actually uses electrolysis to separate alkaline seawater from acidic seawater. But the problem with that is then you have a bunch of acid, and there's not a huge market for acid to change the pH of things. So you're right. When it comes to scalability, the life cycle of these chemicals is very important to consider, where they're coming from, where the byproducts are going. If we're thinking about mining alkaline minerals, you need to think about if those mines are emitting more carbon than can be taken up by the ocean or other carbon dioxide removal techniques, where the energy is coming from. All of this stuff is a big question mark. The field trials right now are really focused on whether or not the chemistry is workable from a standpoint of like, we theoretically know that this should work, but does it in the real world?
So that suggests the question, how are they going to tell? What are they measuring to see if this works?
They're measuring a bunch of different things. So the Woods Hole folks they're throwing the whole instrument laboratory at the problem. They're going to be taking water in through the ship that they're driving and releasing the alkaline solution behind to sample for the pressures of oxygen and carbon dioxide dissolved in the water. They're also going to be looking at how the pH changes. They're going to be looking at total dissolved inorganic carbon, which is all those carbonate ions. They're going to be looking at changes in the marine life in the area. Of course, they're going to make sure that they're not, or they plan to make sure that they're not going to be dumping anything on a whale's head.
Right.
But as long as there's not any big animals around, they're going to dump this solution. And then they will be taking a plankton net and dragging the plankton net behind the boat to look at how these little tiny marine plant-like creatures. Plankton is hard to define. Sorry.
Yeah. Things at the bottom of the food web, how the bottom of the food web is affected by this.
They're looking at how plankton, which is the bottom of the food web, will be affected by this experiment in the real world, because other researchers have already looked at how plankton are affected in microcosms and mesocosms, which are basically containers filled with seawater.
Yes, I liked in your story how you had this vocabulary word, the mesocosms, and started right off with that. I immediately was like, I'm in just so I can find out what that word means.
Yeah, so a mesocosm is basically like a giant test tube, like thousands of liters of water in an enclosed container. And then the microcosms are smaller volumes of water, so more on the liter scale. And the nice thing about microcosms is that because they're so small, you can standardize a bunch of experiments across the world. So you can have a bunch of different labs doing a very similar experiment with different samples of water. So like you can go out and scoop ocean water off the coast of Maine or off the coast of Australia or off the coast of England, right? Like any of these places.
And the mesocosms, these are in the water, but not, the water can't pass from one side of this mesocosm out into the general
Correct.
ocean.
So the 1,000-liter containers, the mesocosms, they are just containers in the ocean. The researchers flood the container, collect all this water, and then make sure that if there are any fish or anything else accidentally get caught up, to remove the fish, because that's too complex. They're really only interested in the plankton, the bottom of the food web. At this point, historically, the research so far has really only been interested at that level. Future research, though, might look at some fish larvae. But yeah, and then that water is totally isolated from the surrounding water. So anything that's added to the mesocosm is contained within the mesocosm. And you don't worry about putting anything into the surrounding open water system.
Yeah, I wanted to ask about that because you encountered some critics, some people that aren't happy about this. Were they worried about the Loch Ness project specifically? Were they skeptical about ocean alkalinity enhancement? Or were they against climate change mitigation as a whole effort?
Yeah, so I think you're talking about James Carey, one of the sources in my story. Yes, he was skeptical about Loch Ness specifically, but also about ocean alkalinity enhancement more generally. Loch Ness, he's not totally convinced that they will be able to measure all the things that they want to measure, because it's just open water systems are incredibly complex. And so measuring anything in the open ocean is going to be very difficult. The signal to noise is very hard to tease out. So he was skeptical about that. But more broadly, I think he has concerns about scalability. And scalability is a big question in all of these things because we are emitting so much carbon dioxide that it almost doesn't pay to do any of this before seriously figuring out ways to cut emissions. The scientists, of course, argue that we need to have a solid research-based foundation to even have discussions about carbon dioxide removal on a grand scale. But others, of course, worry that focusing on research for future applications sort of moves the goalpost for the current needs of just emission reductions.
Yeah, I run into that debate a lot. Like, should we be doing this at all? And it's a lot of the same dynamics of a lot of people think we will need these carbon removal technologies a little bit down the line. But yeah, there's lower hanging fruit that we should be picking, but it won't be ready then if we don't start working on it now. It's a difficult balance.
Yeah, definitely. And again, all the researchers that I talked to were not interested in selling carbon credits, and they weren't interested in trying to make this a commercial sort of opportunity. They're really just wondering, will this work? And the models that climate scientists have run suggest that ocean alkalinity enhancement and other carbon dioxide removal techniques could be incredibly valuable, worthwhile pursuits in the fight against climate change. But without doing these experiments in the real world, in field trials, there's just a big question mark about whether the real world is too complicated for this to work.
I'm going to reveal my chemist background and say I'm curious about at the lab scale, though. I mean, is there solid proof at the liter scale that making the solution more basic will cause carbon dioxide to dissolve into it? Do we have that basis really solid?
Yeah, they figured that out. They are confident that carbon dioxide will dissolve into water more readily if the water is more basic, which is actually part of the reason why the oceans are so powerful already. So the oceans are absorbing vast amounts of carbon dioxide every year, and that's because their sort of inherent pH is around 8.3, which is quite basic compared to other bodies of water. In fact, tap water is often more acidic than that. And sodium hydroxide is often used in municipal water treatment plants in order to change the pH, which helps prevent corrosion from pipes. So, humans are already doing pH modification on our drinking water, and the ocean is already super basic. It's just a question of whether or not we can see these effects in the real world, because the ocean is so huge.
Are there any other characters from your interviews that you wanted to bring in but didn't quite fit?
That's a good question. Yeah, the section that ended up not going into the piece was really about how the researchers are communicating with the public about their work, which was more of like a social sciences kind of discussion. And those folks were all great. And there's some really fabulous social science research happening in this space and really important takeaways, like you need to talk to stakeholders before starting your experiment, which seems really obvious, but sometimes scientists are so excited to go out and start collecting data that it might not occur to them that the people living in these areas will feel very betrayed almost if this kind of science happens without any of their input. And so it's incredibly important to have the local communities involved in the whole scientific process from even before applications for permits are submitted.
Yeah. And so, I mean, how was the community responding to the Loch Ness experiment? I mean, you had your person that was opposed to it because they didn't think it was going to work.
Yeah, so there have been some vocal opponents in the local community, but it also seems like there was potentially less. I mean, there was some reporting that there are local community members who are still not convinced that it's a good idea to put stuff into the water. But there were also, the Loch Ness researchers did take lots of conversations into account and change some of their experimental design based on what the local fishing community said and other stakeholders wanted from the experiment.
Yeah, because I guess this is happening out at Cape Cod, and that is not, it's an area known for a lot of community activism. It's not a quiet, sit back and let everything happen to them kind of a place.
Yeah. The most important thing with all of these environmental field trials is to engage community members early and for the entire time that you're doing the experiment. And do more than, it goes beyond just educating people. It actually requires that they are involved in the decision-making process.
So Cape Cod's not the only place that they're looking at this kind of a thing. There are some other experiments probing this idea of ocean alkalinity enhancement.
Yeah, so the other experiment that I talked about in the piece was really, really small scale, tiny scale off the coast of Australia. They're putting minerals down in the sediment in the water to just see how worms and other creatures that live down there will respond. Their results, this is really recent. It was our winter, their summer, but they just recently finished that project and they told me that their results are promising. The worms don't seem to care. But the scale at which they were doing it is so small compared to what will need to happen. There are companies.
So this is the scale where they're like swimming down there with a single vial. And
yes,
doing, okay.
They're swimming down with a single vial, opening it up, pouring it, and then watching for a few weeks, taking samples every few weeks, and then taking up sediment samples. Obviously, that's such a small scale that that's not what any sort of real world application will look like. We do actually have examples of real world mineral applications. So there's a company called Vesta that has done some olivine trials where they've put huge amounts of crushed olivine sand along, I think it was the coast of New Jersey and off the coast as well. Obviously, tons and tons of crushed rock is a lot different than a tiny little vial of crushed rock. And they're interested in figuring out some kind of carbon credit, some way of making this technique profitable. If there's any future in these sorts of techniques, there should be small scale, very safe field trials before actually approaching anything that looks like what we would need to combat climate change in a real way, which is unfortunate. It's like such a bummer, right? Like the best solution is for everyone to bike to work and go from there.
Stop eating so much meat. Compost.
Yeah. Oh, God. There's this carbon dioxide removal technique where you use electricity to take carbon dioxide out of seawater and pretty much, and then you put that carbon dioxide into the ground, you inject it into some sort of geologic formation. Pretty much everyone thought that that was a very silly approach because the ocean is one of the most stable places for carbon dioxide to live. Carbon dioxide that is sequestered into carbonate, which is all of those sorts of ions that are in the ocean, will stay in the ocean as carbonate for 10,000 years. So it's silly to take stable carbon dioxide out of the ocean to put somewhere else because the ocean is a really good home for it.
So in June, actually, I'm going to visit a pilot rig in New York City where a startup is testing a system like the enhanced ocean alkalinity that you're describing. They're going to add reactive alkaline minerals to remove CO2, this time from the East River in New York instead of the ocean. What should I ask them? What should I be looking for? What?
You should ask them how they're measuring how much carbon dioxide is being removed from the air, how they're measuring carbon dioxide uptake.
All right. So is there anything else to me reporting that you wish you could have fit in somehow?
The one thing that I didn't emphasize, and I would like to have emphasized,
Yeah.
is that a big piece of all this research is what the researchers called monitoring, reporting, and verification. And that goes into sort of figuring out if this is a usable technology for something like carbon credits. And what that means is that you need to be able to monitor how much carbon dioxide is removed. You need to be able to report it, which is a whole different sort of infrastructure that's separate from the science. And then you need to verify it. So other people need to be able to come in and measure the same thing that you measured. And a lot of this research right now depends on modeling. There are very few field trials, although it's a growing field. So there will likely be more field trials in the near future. But monitoring carbon dioxide removal on a global scale is going to be incredibly challenging, which is why these sort of open field trials are so important. Because if you can monitor it on the small scale, and you can prove that you are able to monitor how much carbon dioxide is removed on the small scale, and then other people are able to verify that you are measuring what you think you're measuring, then that basically opens the door to realistic sorts of deployments in the future.
Okay. Well, Fionna, thanks for diving deep on this with us.
Thanks for having me. Thank you so much.
And I usually use that line. It's not always literal, but this time it was.
I was going to say that's a great pun. You caught me off guard with that one.
You can find Fionna Samuels' story about oceans as climate change allies on C&EN's website or in the April 14th, 2025 print issue of C&EN. We put a link in the show notes along with the episode credits. We'd love to know what you think of C&EN Uncovered. You can share your feedback with us by emailing cenfeedback@acs.org. You can find me on social media as @CraigOfWaffles. Fionna, how can listeners get in touch with you?
I'm @FMorningstar on Blue Sky.
All right. This has been C&EN Uncovered, a series from C&EN Stereochemistry. Stereochemistry is the official podcast of Chemical and Engineering News. Chemical and Engineering News is an independent news outlet published by the American Chemical Society. Thanks for listening.